Okay, we are back. So, what have we been talking about? We've been talking about these things called grammars. We started off with regular grammars, then we generalized them to have anything on the right-hand side, and then we came up with context-free grammars, which have definitely more power than the regular languages or anything resembling the regular languages because we can recognize things like 0 to the n, 1 to the n. We can recognize a whole bunch of stuff. So we started off the regular languages we started with this machine model called a DFA. Then we talked about NFAs, then we talked about regular expressions, and then finally we talked about regular grammars. We started off the context-free languages by talking about grammars. So what do you think we should talk about next? Well, we're doing this in the backwards order. We'll be talking about a machine model for the context-free languages. Okay? Well, we want to have something that's equivalent to the context-free grammars in power, in recognizing languages. So let's talk again about 0 to the n, 1 to the n. We proved quite a few times that this language is definitely not regular, so there's no way any DFA could ever recognize this language. So what could we do, though? What could we think of adding to our DFA model, or NFA model for that matter? What could we add in order to recognize something like this? Well, some kind of memory of some kind, and the suggestion was a stack. So how would you use a stack to recognize this language? Like if I had an input that had a bunch of zeros on it and then a bunch of ones on it, how would I recognize that? How would I accept that string if they have the same number of zeros and ones? Yeah, what we could do is put the zeros on the stack, iteratively put them on the stack. If we encounter a 1, then what should we do? Pop it off the stack. So we'll pop a 0 off the stack, and then when we read another one, we pop another one, pop, 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 and then at the end, I should have a empty stack. Let's see. So what operations do I need if I'm going to use a stack? What two things do I definitely need for sure? Push and pop, yeah, there's no way of getting around that. Do I need a peek operation? Look at the top and not pop it off. No. What could I do? I pop the thing off the stack and put it back on. I may want to know the depth of the stack, but we're not going to actually keep a counter here. What's sorry? Well, we wouldn't know in general. Like you wouldn't know the length of the input that you just processed in the DFA. It's the same thing here. In fact, if you put a counter on this, it becomes more powerful than the context-free languages, believe it or not. So, yeah, so we're not going to have a counter on this just yet, or ever really. So we don't need peek, so we can simulate that with pushes and pops. Do I need an empty stack operation?
Yes.
You sure?
Depends on how big the stack is.
Or a check for empty stack operation, let's say.
Oh, but not, if it's defined by the language, you wouldn't need it because technically it should just be empty. If it was like an actual string in the language.
Well, suppose this. Let's start off with an empty stack. Well, at some point through the computation, I'm pushing and popping and whatnot. What if it encounters the empty stack and it tries to pop? Then it should not work anymore, right? Well, let's see. How could I avoid that problem? Since we only have pushes and pops, maybe what I can do is put a special symbol on the bottom of the stack. And any time where it would have normally been an empty stack, it sees that whatever symbol, this special symbol, And since we only have pushes and pops, it could only pop that character in order to do a transition, or not pop at all, if we want to generalize it. So if we put that special character on and then pop it off at the end when it's supposed to be empty, then that would be a way to check for empty stack. So I don't actually need a check for empty stack operation. Pretty cool, huh? So let's work with this. Let's work with these two operations, and then we'll try to come up with a model of computation for this. Should I allow you to, let's say, push something on and not pop anything in order to generalize it? Yeah, that seems entirely possible. What if I didn't want to push or pop on that transition, do nothing to the stack? That seems logical too. What about any combination of push or not, pop or not? Yeah, all those combinations are possible. So we want pop or not and push or not. So we need to think about some other things. Well, like with DFAs and NFAs, we had this really intuitive idea of what can appear as the input to the machine. We had the alphabet sigma. Should I allow you a different alphabet possibly for what can appear on the stack than what was in the input?
What do you mean by entries?
Could I have like a separate alphabet entirely only for the stack? Sure. In fact, I think if you limit it to be the same alphabet, you don't get all the context-free languages, but I'm not going to say that as a theorem. But so another thing that we want is a quote-unquote stack alphabet. Okay, that may or may not be the same as the input alphabet. Okay?
Are we going to define that a little bit later?
Yes, I'm actually going to define it now. Oh, well, in a minute. So what these things were called way back in the day are called push-down stores. So the idea is that you pushed something onto the, so I don't think it was called the stack, it was called something else, but you pushed down onto this thing and you were able to read only the thing on the top of this, what would we call a stack. So they were called stores before, but since it's a generalization of the automata that we've been studying, what do you think these are called? Pushdown automata. So a pushdown automaton, PDA, not a public display of affection. Yeah, it's a in-joke among my recitation sections. All right, so is a something tuple, and it's going to be a long tuple. Well, since it's a generalization of DFAs and NFAs, I should have states, right? I should have states, no problem. So Q is going to be defined the same way. We're also going to have an input alphabet, just like DFAs and NFAs. Going to skip one. I'll get to that in a second. Well, since this is an automaton, we're going to have a transition function between the states, just like before. Transition function delta, start state Q0, and final state F. Exactly the same as before, although delta is defined slightly differently, but the tuple's written the same way. So this is going to be a 6 tuple. So as was suggested earlier, the thing in the middle, the third element, is going to be the stack alphabet. And we're going to denote that by gamma, capital gamma. I think it's capital. Please be capital. Yes. Phew. All right, where Q, sigma, Q0, and F are the same. Gamma is a finite alphabet called the stack alphabet. Oh yeah, that was the thing I was going to talk about. Okay. Yeah, so gamma is a finite alphabet. Well, what thing have I formally defined yet? The transition function. I haven't formally defined how we're going to relate the stack in terms of doing transitions. So let's see. Well, we may have a transition possibly when we make a thing, or make a PDA, that does a push and a pop on the same transition, let's say. Which one of those two operations should I do first, the push or the pop? Be very, very careful. If I pushed first, the thing I wanted to pop is where? Below the top now. So what should I do first? The pop operation. And then the push operation. Okay? So we're going to design the transition function like this. We're going to have a state, an input symbol, and some character that's on the top of the stack to be popped. Then we'll execute the transition by going to one of many possible states and some possible thing that may be pushed onto the stack. Okay? So we're going to design the transition function just like that. Q cross. Well, we're going to generalize an NFA here. So we may have an input character to read or nothing to read. So we're going to have cross sigma union the empty string, just like before, no changes. But instead of having a character to read, now we need to worry about the thing that may or may not be popped. So how would I dictate a character to be popped or not in this setting? Well, pick a character out of gamma or not. How do I say not? The empty string. Exactly like with sigma before, but now with gamma. So cross gamma union the empty string. So it's just a generalization of NFAs where we can have a character to pop or not. So this represents the pop operation. So pop always goes first. Okay? And then this is going to produce something. Well, since it's a generalization of NFAs, what is the transition function of NFAs output? Set of states, and we denote that here by a, starts with power and ends with set. Yeah, power set of what, though? So what was it for NFAs before? The Q, right, because we didn't have a stack to worry about, we can go to any subset of the states any subset of the states is possible. But here, we need to worry about many possible states we can go to, as well as characters that may or may not be pushed in this setting. So we're going to cross this with gamma union the empty string. And so this guy represents push. Okay? Any questions about that? So let's do an example. Yeah, that's the notation. All right, so I want to recognize, so make a PDA for 0 to the n, 1 to the n, and at least 0. So I clearly can't use an NFA for this because no NFA can make this language. So I need to incorporate the stack in some way. Well, let's see. Our idea was keep pushing the zeros on the stack, and then once we start seeing the ones, we're going to match them off with the zeros, and then if we have an empty stack at the end and have no input left to read, so that's important, no input left to read, then we should accept at that point. Okay? Well, let's see. What could we do? We need to check for the empty stack at the end. So what was our idea to check for an empty stack at the end? Put a special character on. So let's make a start state, Q0. Well, when we're pushing this special character on, should we read anything? No, why shouldn't we read anything? What's that? We'll worry about that later. Well, we'll put it on there, but why should I not read anything? Because the places where I'm going to be reading stuff are when I'm pushing the individual characters 0 and 1 on the stack. Because our idea is, once we see a 0 on the input, put it on the stack. But what we're doing here is putting a special character on. So that's not the process of seeing a 0 or a 1. So I shouldn't read anything on the input. Should I pop anything? No, because what does the stack start out as? Empty. So if I pop anything, we're stuck at the beginning. So this first transition will be, so the format of transitions for PDAs is what we read, so empty for reading, then comma, whatever thing that we pop, which happens to be empty here, and then with an arrow, we put the thing that we're going to push. And so the common special character that is used for a special symbol is called a $. But any character will do here. So what is the stack alphabet going to be for this PDA? $ and 0 and 1. Because actually, we actually don't need 1 here, believe it or not. Because we're only matching them up with the zeros. We're not putting the 1s on the stack. So, but I'll include it anyway because there's no reason not to. So our stack alphabet, because we're putting the $ on the stack and eventually putting the zeros on the stack, we need a $ on in the stack alphabet. All right, so this goes to a state. So once we put on that special symbol on the stack, then eventually at the end, once we do all the processing with the zeros and 1s, then we'll check if that's the only thing on the stack and our input's empty. Well, once we put that thing on, what is my next step? We'll start reading the zeros, hopefully, start reading the zeros. So how many zeros might I read? I have no idea. So what should I do in Q1 then? I should make a self loop because I don't know how many I'm going to read. So I'm going to make a self loop here. So am I going to read anything on this transition? The 0. Yeah, so 0, comma. Am I going to pop anything on this transition? No, because the $ is the only thing on the stack. And if I pop it, then I just lost the thing I had there that I wanted. So I better not pop anything. Should I push anything? Push a 0. Okay? So as long as we're seeing zeros on the input, put them on the stack. But now we got to worry about if we see a 1, then we need to start matching them up with the zeros on the stack. So, any idea how we're going to do that? I need to go to some other state. Because if I stay here, then if I see a 0 after a 1, then that's not in the language. But I may accept after that. So I definitely need to go to some other state. So here's an important question. Should I read anything on this transition? I mean, I could, but What string would I avoid in this language if I did that? What's our favorite string? Empty string. If I read something on this transition, would I ever accept the empty string? Right. So I better not read anything on this transition. So I'm going to non-deterministically start guessing. I'm going to start seeing a 1. Should I pop anything on this transition? No, because this doesn't correspond to the two things I want to do. Should I push anything? No. So this is what this is my term, no one else's term, called a triple epsilon transition. We're going to be using transitions like this quite a few times, so I'm going to say triple epsilon for that. Copyrighted, yeah. Trademark, too. Patent pending. Yeah, we have triple epsilon here because I need to accept the empty string. So if I read something on that transition coming down, then there's no way I could have accepted the empty string. If I read on that transition coming down, I'd have to make Q1 a final state. Right? But I need to match them up with the 1s. Yeah, so the way that the empty string is going to work here is that it's going to zoom here, zoom down, and then eventually zoom over to a final state that we'll make in a second. But the empty string needs to be accepted. If I said here n strictly greater than 0, then you're right. I could read on that transition. Yes?
So you read initially, not initially.
I can't hear you, sorry.
Did you read initially from Q0 to Q1? Did you read that epsilon?
No. So we're not reading anything on that transition. The one that he was referring to is the one coming down to Q2. Why am I not reading anything there? Because I need to eventually accept the empty string. So that's why.
So, did push an epsilon?
So this is a thing that many people say, like I read an epsilon or I pushed an epsilon. This just means not reading, not pushing, not popping. Yeah. So this transition literally will do nothing to anything. Yeah. It's the laziest transition ever. All right. Yeah.
It's like similar technique as what we did with NFAs. Is that kind of what we're doing here too?
Similar in what sense?
Similar in the sense that like now we are in state Q1.
Mm-hmm.
It's also possible that we can just
Yeah.
like reach Q2
Yes.
without needing to do anything.
Yeah. We won't be doing any kind of epsilon closure thing here because it'll turn out that deterministic PDAs are strictly less powerful than non-deterministic ones. So we can't actually convert this in general to a deterministic machine. But you're right that in the sense that it has a non-deterministic choice to make. You're correct on that. Other questions? All right, so I must come down to another state in order to process the 1s. Well, I may see a whole bunch of 1s. I don't know how many. So like before, we're going to have a self loop. So what should I do on this transition then? I should read a 1. Yeah, because I'm going to be seeing 1s. Should I pop anything? 0. Good. Should I push anything? No, I should not push anything. Because if I push something, then the 0s are now below the thing I just pushed, and now I've altered what was on the stack in a way that I don't want to. Well, let's see. If everything matched up, what should be on the stack now? $sign. How do I check if $sign's on top of the stack? Pop it. That's the only way I could check. So I must go to some other state. Should I read anything on this transition? No, because hopefully I've read everything I needed to before. I must pop the $sign. Should I push anything? No, but could I? I could. I won't here. So the rule that we'll play is that the stack always starts empty, but it does not have to end empty. It could, but it doesn't have to end empty. In this case, it'll always end empty. So we'll come to Q3, and this should be a final state. Okay? So remember the rules of acceptance here. First of all, I have to be in a final state for sure. But the input has to be fully consumed in order for me to get to Q3. So is this PDA correct for that language? What's that? It's incomplete? How? It's not a deterministic machine. Yeah, these are non-deterministic machines. In fact, when we define deterministic PDAs, there is one for this language, but not in general. Yeah.
You said that the stack could end empty, but it could not end empty.
Yeah, it's possible that it could.
So you could end in Q2 state and Q1 state.
What's that?
So you could end in Q2 state, Q1.
What do you mean end in?
I mean, your input would end.
Oh yeah, yeah. So like if I was in Q2, like I've been processing some ones and then I see a 0, then I'd be, the only thing I could possibly ever do is go over to Q3, but the input's not fully processed now. And so therefore I can't accept, or the machine won't accept. Yeah, so the rules of the game are, it ends in a final state and you've read all the input. Well, let's see if it's correct. Yeah, go ahead. Yeah, great question. So that's for the correctness reasons. So what if I had zeros followed by ones and there are more ones? Well, let's trace through the computation. If I see a 0, then I'm going to be putting all the zeros on the stack. Then when I start seeing the ones, then I'm going to be popping off the zeros. But as you said, there are more ones than zeros. So what's on the stack? $, and what's still on the input? 1. So I can't do that transition 1, 0, epsilon because 0 is not on top of the stack. So the only transition I could ever do is going over to Q3 and popping the $sign off. I'm in Q3, should I accept? No, why? I haven't read all the input. So that's one case. What if we had more zeros than ones? So I'd be pushing all the zeros on, no problem. I come down to a Q2 where I read all the ones and pop the zeros off accordingly. Well, let's say the input's fully processed now. What's on the stack? 0. I can't go over to Q3 because it's not a $sign on top of the stack. And I can't do Q2 because the input is fully processed. So therefore, I can't do the 1, 0 epsilon transition. So the machine, like an NFA, it just becomes stuck. It's not a valid computation. Okay? Any questions about?
Do you have to like draw a state to the next state?
No, because these things are non-deterministic.
Oh.
Mm-hmm. Yeah. So yeah, these things are completely non-deterministic. Yeah.
So we don't have to add any states to correct that because it's non-deterministic. It just ends up getting stuck.
No. Yeah. Correct. Mm-hmm. Yeah.
The case where we had more ones and zeros, we would never reach the $sign, or we wouldn't reach $sign.
No, I would reach a $sign on the stack. So, but if I did that transition over to Q3, I still have more input to process because I have more ones than zeros. And so therefore, I won't accept because the input's not fully read yet.
What defines that?
That's the definition of PDAs. Well, all the machines that we've seen, DFAs, NFAs, we had to read the entire input first in order to accept. Because we defined computations as the entire input being processed.
So you don't go to Q3 because you haven't read all the
No, I can go to Q3 as in like literally transfer over to the state, but I won't accept the input at that point. Yeah.
So how would one draw a transition table for this?
Great question. So I would really avoid making transition tables for PDAs. But if you were so minded, so let's cut and paste this guy. Yeah, go ahead.
So when we have 0 epsilon and 0, so the first 0 for on Q1 stands for
Read
what
it.
we read
Mm-hmm.
from the input, and then the epsilon stands for what we pop,
Yeah,
and then the last one stands for what we
yeah, what we push. Mm. Yeah. Yeah, so pop always occurs first and then push. Mhm. Yeah, so it's read, pop, push in that order. Other questions? Yeah.
Is this kind of like saying if you read a 0, then you pop, or sorry,
It pushes 0?
if you push a 0,
No. So if you see a 0 on the input and you see or not see whatever's on the stack, then you can apply this transition.
okay.
So these things are non-deterministic. Yeah. I should define it formally. But what was asked first was the transition table. So as these things are non-deterministic, what does the transition function output? A set of, well, it's not states anymore. It's not a set of states anymore. It's a set of pairs where the first coordinate is a state and the second one is the thing that's pushed on that transition. Because if we look back at the formal definition, it was the power set of a cross product. So it's just a set, it's just a set that has pairs where the first guy is a state and the second one is a symbol or the empty string. So if we go back to here, let's talk about, so let's see. I wasn't thinking of doing this, but let's try it anyway. All right, so Q0, Q1, Q2, Q3. Well, all the possible inputs are 0 inputs. I mean, like the things that could appear on the input part. 0, 1, or epsilon. Well, does Q0 on 0 have any transition? No, this is not correct. It's going to have many more columns. So since we need to consider all of the inputs as well as stack characters that could happen. So we would have 0, 0 for thing that is read and popped, then 0, 1, then 0 $, because that's on the stack, then 1, 0, 1, 1, I'm running out of room, $, and then empty string 0, empty. You see why to avoid these? Yeah, but we should do a few of these at least. So remember, this is the thing that the coordinates at the top represent states that, the thing that's read or not, and the thing that's popped or not. And the entries of this are going to be sets of pairs of states with the thing that's pushed in this case. So does Q0 have any transition where you read a 0 and pop a 0? No. So this entry is what? Empty set. In fact, most of these are going to be the empty set, which is nice. Well, what about, let's zoom over to this entry right here, 1, 0. This, and not for Q0, let's look at Q2. Does Q2 have a transition where it reads a 1 and pops a 0? Yes. So this is not going to be the empty set anymore. Well, it's going to be a set always. I should leave a little more room. Well, it's a set containing pairs, so it's going to have a pair. Since there's only one transition of that form, it's going to have only one thing in it. Well, what state do you go to and what do you push? Q2 and empties. Yeah, so what you put at the top for the columns are the things that you read or not, and things that you pop or not. Yeah.
You also need a column for 0 empty string. Like 1 empty string.
Yes. Yes, so you would have 12 columns in this case. No. That's why I always said use a state diagram. Yeah, I would never ever require this on a homework or a test or anything. Always use a state diagram.
You don't have to keep going.
No, but it's important to understand. It's important to understand what the formal structure of the PDA is actually doing, and knowing that because it's actually important to understand how this works. Because when we talk about DPDAs, it's using a lot of the structure underneath here. So a little bit of understanding is good, but state diagrams are far easier to understand. Cool. Any questions? All right. So as we discussed, we wanted this to be the model for context-free languages, right? We wanted to have PDAs recognize the same languages as context-free grammars. We haven't proved that. We have proven that if we ignore all of the pops and pushes, what languages do I get? Just the regular languages, yeah. So I get at least the regular languages, so that's good. But I definitely get more because I have 0 to the n, 1 to the n. But the question is, do I get all the context-free languages? And the way we're going to prove that, in fact, the answer is yes to that. So we're going to prove in 2 directions that PDAs and CFGs are equivalent. If I want to prove that 2 models of computation are equivalent, how do we know how to do that? Right. I need to show you how to convert an arbitrary CFG and make a PDA out of it with the same language, and convert an arbitrary PDA into an arbitrary CFG. Okay? So we're going to do the easier direction, hopefully by the end of today, which is convert an arbitrary CFG into an equivalent PDA. So I have this thing, this CFG with a bunch of variables, a bunch of terminals, rules, as well as the start variable, and I need to make a PDA out of it. So let's look at the grammar that we had way back here. Let's copy, do I have it? No, I don't have it. So let's look at the grammar. It doesn't have to be in Chomsky normal form, by the way, but let's consider the grammar of balanced parentheses. So the one we had was left S right, or SS, or empty. And let's say we want to derive the string left, left, right, right, left, right, which is a balanced set of parentheses. Well, suppose I wanted to make a PDA for balanced parentheses, let's say. Well, this language is not regular, so I need to use the stack in some way. Well, let's see how we would derive the string. So we would start at S, then we need to go SS, then let's say we're replacing the left one. So here's actually a place where leftmost derivations will come in very handily. So we're going to be replacing the left S first, which means that I'm going to have left S right S, and then this guy is going to make left S right S. Then the first S is going to now disappear. So left, I replaced it with empty, S, and then left, right. And then we did the left S right here, and then now we made it go away entirely. And then we have a string full of terminals, and therefore we're all good. So that is a derivation of that string. Questions about that? So I want to mimic this on the stack in some potentially clever way. I want to put this derivation on the stack and do pushes and pops in a hopefully useful way so that I can do a derivation. So here's something that's really important. When I produce a terminal, so in case of like these two terminals right here, are they going to ever change? No. So the grammar is generating these terminals, and they're never going to be replaced by variables. Oh, what would a PDA do if it happens to see, let's say, a left parenthesis on the stack? Well, where am I going to be matching it up with? Off of the input. The input's going to be provided with this string, or a string like it, and we're going to be trying to do some kind of derivation maybe on the stack. Well, since this left parenthesis that would have been made by the grammar is never going to change, I think I should match it up with the input and pop it off the stack, because that left parenthesis is never ever going to change. But let's say that if I happen to put this on the stack and I see a variable at the top, what would I do with a variable here in the derivation with the grammar? I would apply some rule with it. So what would be a good idea is, if we see a variable on top of the stack, I'm going to take it off the stack and put on the stack in some way one of the right-hand sides of the rules. So let's actually see this in action. So we start off with an empty stack, no problem. And then what we may want to do is start with the start variable on the stack. So we're going to put S on the stack. And then now we need to make an important distinction. So our idea was we're going to take the variable that we see on the stack off the stack, and then we're going to put on the stack in some way one of the rules on the right-hand side, in this case, SS. Which order should I push them in? Remember, leftmost derivations. I'm going to push the right side first. So I'm going to push this S first after popping this guy off. I'm going to pop that guy off. So it's not going to make much difference in this particular case, but it will in the next one. So I'm going to push the entire right side. Yeah, go ahead.
Why is it that you start with the right? And put that first?
Because I'm doing leftmost derivations. If the PDA is presented this input right here, which order does it read it in? It reads it from left to right. So the things on the left better be on the top of the stack, which means that the things on the right better be on the bottom. Okay? So when we make this SS right here, we want the right S to be on the bottom and the left one to be on the top. Okay? Well, it doesn't look very different here, but it will in the next one. Well, we see a variable on top of the stack. What do we do with variables on top of stacks? Pop it and then push on the right-hand side of some rule, in this case left S, right, on the stack. So I'm going to put this on the stack. Is this bottom S going to change? No, it's not going to change. So what thing is above that S right now? The right parenthesis. Because I want the left one on top. Yeah.
Could it be very soon that this dollar?
We'll talk about that. Yeah. Other question?
How are you reading the right one first or pop it on?
We're going to design the PDA in such a way that it does the push of the right guy first. And then we're going to have a special state which represents, we're going to examine what's on top of the stack. And then if it happens to be a variable, we go out. And then we're going to be pushing the right-hand side of that variable until we, the right-hand side of that rule until we get to the left side. And then we come back to the state. Yeah. Other questions? Okay. So we want to see the right parenthesis next, then the S, then the left parenthesis. Oh, there's no variable on top of the stack. There's a terminal on top of the stack. What should we do? Pop it, and what should we do with the input? Match it up with the input. Because the input's going to be provided this particular string there, we want to match it up with a derivation that we're doing on the stack. Isn't that really clever? We're doing a derivation on the stack. And how do we know which of the rules to apply? We don't. Non-determinism takes care of that. Just like how CFGs can apply any rule non-deterministically, PDAs work exactly the same way, non-deterministically, by choosing one of the paths that we're going to create non-deterministically. All right, so we're going to pop this off. I'm not going to do the whole thing, but we're going to go part way through. So we pop the left parenthesis off and match it up with the input. And then now we see a variable on top of the stack. Then we're going to apply left s right again. And then we're going to proceed from there until when? The stack better be empty. Well, if the stack is not empty, it's either there's a terminal or a variable on top of the stack. If it's a terminal, then have we done a derivation correctly? No, because it would have non-deterministically chose the right thing to do anyway. Well, what if it was a variable? Well, the only thing that the variable could do is produce the empty string. In which case, it would have done it anyway, because we would have chosen that path. So the stack must be empty if we did all the derivations correctly. How do we check if the stack is empty? Well, we don't have a way except at the very beginning put on a special character. So right at the very beginning, we're going to put on a $sign or a special character. So a $sign is going to always exist at the bottom of the stack until, supposedly, when we matched everything up correctly. Okay? So I'm not going to do this formally, but let's actually make a PDA for this guy. So let's copy this guy in.
I have a quick question.
Yeah, go ahead.
You said that the stack does have to be empty. If you're able to derive, so say like you have a grammar, you want to derive a string AB, then AB is the same thing as AB with like 10 empty strings after it, right?
Correct.
So if you have like a variable that can derive empty string, and you end up with that variable, a bunch of that variable, can you just say like they're all empty
Well,
strings? So
because of non-determinism, it will choose the right thing to do. It'll make all those variables disappear. Because we'll design it in such a way that the only way to get to the final state is popping that special symbol off, in indicating that we did everything correctly. Any questions otherwise? All right, so let's make a PDA for this guy. So what is the very first thing that we should do? Push the special symbol on. So read nothing, pop nothing, push the special symbol on. Let's call this Q1. Now what should I do? Well, is there a variable or terminal on top of the stack? Is the start variable on top of the stack, though? Not yet. What should I do next? Push the start variable on. I need to start somewhere. Because all derivations start with the start variable, we put that guy on first. So I'm going to have a very similar transition, but without the vertical line, I guess. All right. So I'm going to call this state in the middle Q loop. Well, let's see. Either a terminal or a variable can appear on the stack, or the $sign, but we'll worry about that later. What if a left parenthesis appears on top of the stack? What was our idea? Pop it and what? And match it up with the input. Should I push anything? No, because we want to access the things below that anyway. So Q loop is going to represent the state where we come back every time to examine what's on top of the stack. So I'm going to make those guys self loops. So if I see a left parenthesis, oops, on the input, I better pop a left parenthesis off the stack, and I better not push anything. And also the same thing for right parenthesis. Okay? So I'm going to let you know right now, these two transitions are the only transitions that'll read. No other transition reads, other than these two. And the reason we want that is that when we produce terminals in the grammar, those are the only terminals that we are going to produce by the grammar, and so therefore we want to match those up exactly with the input of the PDA. And so therefore these two transitions should be the only ones that read. Yeah. No. No, because that corresponds to it could be a partially empty derivation. Yeah. Other questions? A Q loop represents the state where we come back over and over, where we examine what's on top of the stack. It's either going to be a terminal, and in this case a left or right parenthesis, or a variable. And then in this case we're going to have multiple possibilities of transitions when we have when we see an S on top of the stack. We're going to have multiple possibilities. Other questions?
What is the significance of calling it Q loop? It's called a Q.
Yeah, the name doesn't matter. Yeah. I think it's called that in the book, if I'm not mistaken. All right. Well, we need to now incorporate the case of seeing a variable on top of the stack. What variables could we see? S. Well, we need to be able to apply one of those three rules. So we're going to have three paths that go out and come back. So let's do the S to epsilon one first, because that's the easiest. Well, what I should do is go out and pop S off the stack, and then come back pushing on what? Nothing. Yeah. So I'm going to come out here without reading, popping the S that we see off the stack, pushing nothing because all we want to do is pop S off. I'm not going to name that state because it's not important. And then once we, the only thing that we're going to need to do is not push anything. And so once we're done not pushing anything, what state should we end up back at? Q loop. And so therefore, I come back there with a triple epsilon transition. So in the grammar sense, this simulates if I happen to see an S, I apply the rule S goes to empty. So that means if I see an S on top of the stack, that means just replacing that S by popping it off. Okay? Now let's do the more interesting ones. So we handled that guy. So let's handle S to SS. So what is our goal? I want to make this process algorithmic. So what should I do first? Pop S off. Then what should I do? Push an S, then push an S. How many characters can I push or pop in a single transition? 1 or 0, but at most 1 for sure. So I'm going to need 2 states here. Got to go out to pop S off. 1 to push a single S on, then one more to come back to Q loop. So I'm going to make some room because these get cluttered really fast. So I'm going to have epsilon S to epsilon. And then the stupidest transition next, where I'm going to push back on the same thing, but I want to make this process completely algorithmic. And then I must now come back to Q loop by pushing on another S. And of course, I know I'll have some people who say, well, you pop that S off and then you pushed it right back on. You fool. Why should I do it this way?
No mistake.
Well, it's much easier to verify correctness this way. And it's algorithmic because the transitions that come out are going to be always the same. Not read, pop whatever the variable is on the left side, and push nothing. Then all the transitions coming back, eventually coming back to Q loop, are pushing the right-hand side in reverse order because we want the left-hand side on top. Okay, well, we got that guy done. Let's do this guy left S right. So I'm going to come out here, way out here. So thank goodness this is the last path coming out. Epsilon S to epsilon, because we needed to pop S off. Which character should I push first? The right parenthesis. Good. So I need to push the right parenthesis on. My handwriting's getting sloppy. And then what do I need to push? S back on. And then I gotta go all the way back to Q loop on pushing the left parenthesis on. We're not completely done. There's only one more state. So think about what we're doing. We put S on, then if we see a variable on the stack, then we apply a rule on the stack, essentially. Then if we see terminals on the stack, we just pop them off with the input. And then if we see a variable, we do that again until hopefully we run out of input and the stack now has a $sign, right? So if I see a $sign, what should I do? Go to a final state. So I better go to some other state on not reading because I better only read on the self-loop transitions. $sign to pop it off, and doesn't matter whether I push or not. In some state that's final. Okay, does that make sense? So in this process of converting a CFG to a PDA, these four states, Q0, Q1, Q loop, and that final state, are always going to be there, always. And you're going to have self loops on every terminal, in which case you're reading and popping, not pushing, whatever the terminal that is. And for every rule, you're going to go out by popping the variable on the left side, and then push on the right-hand side until you come back to Q loop, and make a separate path for every single rule. Because I don't want to confuse two different paths. Just like in the fourth, is it the fourth step? No, the fifth step of Chomsky normal form conversion. We didn't want to reuse variables in the case of correctness reasons. Here, I don't want to reuse paths for correctness reasons again. So let's just check if I'm not fooling you. If I had a derivation before, do I have a computation here? Well, let's check. Well, every derivation must start with what? The start variable of the grammar, which is s in this case. Well, s is on the stack because I pushed it on from going to one to loop. Well, if s is on the stack, then in order to process the whole input, I must have done a sequence of derivations in order to get that input. Well, how did we get the derivation rule, the applications of rules on the stack? Well, we applied them in reverse order so that we can process them top to down, which means when in the derivation we process them left to right. So we actually are processing the derivation here, but just in a stack. Well, let's just make sure I'm not cheating when we're accepting. Could I accept if we didn't have a derivation before? Well, let's check. The only way we could have gotten there is if we pushed on the $, pushed on s, potentially did other things, and then popped the $sign off. Yeah.
Say we have another set of rules. Does that mean we have another set?
Yeah. You have one of these for every single rule. Yeah. So can a computer do this? Yes. Because it's completely algorithmic. Those 4 states in the middle, those are always going to be there. The self loops are always, there's going to be one for every terminal in the grammar. And there's a loop for every single rule in the grammar. And so the process is completely algorithmic, so a computer can do this. But could I accept if I didn't have a derivation before? Well, if I had a derivation, we know that each rule application is one of these loops. And if the derivation was not correct, either we have something other than the $sign on the stack, or we didn't read the whole input. In which case, if we went over to the final state, we wouldn't accept anyway, because we didn't read the whole input. So therefore, this process is correct. Does this process work for any CFG? Yes, because those 4 base states are the same, the self loops are the same, and the paths out and coming back are exactly the same. So this works for any CFG.
Yeah, that's this is a generic derivation for any CFG.
No, it's for this particular grammar. The process makes this PDA.
For matching parentheses only.
Yeah, for this particular grammar right there. Yeah, but if you had a different grammar, it will make a different PDA for sure. But you can figure out. Well, the process is almost exactly the same. The only thing that's different is what labels are on the transitions and how many there are and how many paths there are. There's no difference otherwise. Like those transitions from 0 to 1, 1 to loop, and loop to the final state, all of those will be exactly the same no matter what, except for s, because the name might be different for the start variable. But the transitions are exactly the same. So this works for any CFG. So therefore, we proved a result that, no, we actually proved the,
First,
yeah, we proved that the result that I said above. So
an arbitrary CFG goes. So this is an arbitrary CFG?
no, with this example, we were able to see that it works for any CFG. So, I mean, I can define it formally in 3 minutes. But the process is exactly the same, and I know it's formally proved in the book. All you have to say is that those 4 states are in a set of states. You make a transition from Q loop to Q loop on terminal to epsilon for every terminal in the grammar, and for every rule you add a new state. So if the right-hand side has length n, then you add n minus 1 new states, where you go out to that first state where you pop the associated left variable, then you push on the right-hand side in reverse order, and then come back. But yeah, so the process can be made formal, but yeah.
The reverse order being
What's there?
the reverse order being
Yeah, so if the rule was of the form W1, W2, and I'm not saying that W1 through Wn are terminals, they can be anything, then you push on, so push Wn, push, so I'm being informal here for time, but then you push on W1. Yeah, other questions? So we proved that you can convert any CFG into a PDA. Now we need to prove that you can convert any PDA to a CFG. And so there's literally no way I can do that in 1 minute. So I want you to think about it for a second. So what we're going to do is we need to look at an arbitrary PDA that might not be of this form. So you need to think about, well, how does the stack height change over time? And if you can match two transitions where one pushes and one pops, then those must push and pop the same symbol. And therefore, you can make a rule in the grammar for that. So think about it for a little bit, and I'll see you on Monday.